Thank you very much for having me here. We will shift spheres, as you can already see from the animation on top. I'm really mostly focusing on the atmosphere, and what I will talk about today is some results, how the ocean and how eddies in the ocean are reflected on the atmosphere, but otherwise also focusing very much on what high resolution can give you in the atmosphere specifically. And then at the end, I will summarize a little bit our efforts at ETH towards high-resolution Earth system modeling. So I think often, if we look at climate change traditional climate modeling, traditionally, we look at maps like this. This is global average precipitation, very smooth. Probably all of you are familiar with this. And then we try to calculate biases. We saw this in the previous talks. And try to tune the model towards what we see in observations. Normally, if you come from the weather side, if you come from the weather side, you're mostly looking at these kind of maps. And I have to click one more time, and you can see this is really what precipitation looks like on a hour-to-hour basis. And then, of course, if you average long enough, you should get to something that's in the corner here. And the problem is, if we don't start getting this processes right, we have the risk that we get to the right climatology with the wrong features. So that's why I think it's really important, Pierluigi already alluded to that, to really closely work together on this interface between weather and climate. Because I'm pretty confident this is also the scale which impacts us as humans most. The smaller scales where we really have thunderstorms, frontal systems, and so on. And I think you can translate this quite well into the ocean probably as well. So if you can already see, I'm atmospheric biased here. But I like these diagrams where you basically show different scales of atmospheric motions against the time scales and spatial scales. And with GCMs, traditionally, this is basically where CMIP lives. You're in this top right corner. So you can simulate global waves pretty well. You start to simulate synoptic scale features quite well, but everything else has to be parameterized. So for example, the whole mesoscale, convective scale, turbulent scale has to be parameterized. In the modeling, the weather forecasting framework, we're mostly focusing on this area here. So mesoscale processes, thunderstorms, orographic flows, and so on. And then, of course, we have a third box here. This is really mostly focusing on process scale understanding, turbulent models, really resolving eddies in the atmosphere, and so on. The problem really is the atmosphere doesn't work like that. The atmosphere works across all of these scales. And it's problematic, or it's very difficult to parameterize one spectra without deteriorating your simulations. I will show you some examples here. So let me give you a simple example. Let's imagine you're standing at the ocean, you're looking out on the sea, and you see this black cloud coming towards you. There's a forecast for extreme rainfall happening. Like this small scale storm is part of a bigger system that you can see here. We can classify this as a mesoscale convective system. So clouds are organizing on larger scales, and this is even a part of a larger scale weather pattern that we observed in 2023, where you can see this omega block. You had a high pressure system and surrounded by two low pressure systems. Both low pressure systems actually caused extreme rainfall and flooding. The high pressure system caused a heat wave. And this particular pattern, probably all of you might remember that because this caused the flooding in Libya that caused a lot of lives down there. So resolving these models or this phenomena is really important for impact research as well. So the goal here is really to simulate the climate system at local scale granularity globally. And of course, that's a high order. So what we do at the moment, the climate modeling sphere is really expanding towards the lower right corner here. And I wanted to show you some early results that use similar models that you use in EERIE at 10-kilometer scale in the ocean, 20-kilometer scale in the atmosphere, that come from the National Center for Atmospheric Research, where I was working before I joined ETH. And just to show you some flavors what's going on in this community in the US. So what we were working at NCAR with is the Community Earth System model that many of you will be familiar with. There is a high resolution version. It's an older version, 1.3. And what we have used in the last couple of years is a standard model setup, which we use for CMIP. It's 1 degree atmosphere, 1 degree ocean. But then we also have a 0.25 degree atmosphere and a 10th degree ocean model. And one of the most exciting studies I saw in the, let me remove this box here because you can see this as well, obviously. So one of the most exciting studies I saw, and maybe some of you know this, is by Steve Yeager et al. This is a decadal forecasting study, actually. So it's not a climate study per se, but they try to forecast the state of the ocean and the atmosphere a couple of years out. So what you see here in the top figure is the trends from 1979 to 2017. In the left corner is the temperature close to the surface, precipitation in the middle, and sea level pressure. So you can see quite strong trends in the observations. If you look at the CMIP models, for example, and I think this is now, oh, this is not CMIP, this is the 1 degree version of the CSM model, but this is very reflective to the CMIP models as well. You can see that these trend patterns that we see look quite different. Specifically, if you look at the tropical Pacific, the eastern tropical Pacific, there's almost no trend in observations in temperature, whereas the models are warming quite rapidly there. This has related effects on precipitation and on pressure. This is called the pattern scaling effect. Many studies have focused on that. Seeger, for example, Seeger et al., they looked at trends in the tropical Pacific, temperature trends, and basically found that all the CMIP models, or almost all of them, cannot capture the observed trends. Like the observed trends are really outliers in our multi-model ensemble. That's extremely problematic. When we ran a 0.1 degree ocean, 0.25 degree atmospheric model, you can see that the trends match much better to what we observed. And this is now forecast years 1 to 5, so already after, like you lose a lot of the information already after initialization. But you can see now, like in the tropical Pacific, we're much closer to the observed trends. The precipitation trends are much more similar, and also the sea level pressure trends are much better simulated. And they attributed this back to a better resolution, a better representing ocean currents and ocean processes in the Southern Ocean, close to Antarctica, which I found really fascinating, that small mesoscale oceans influence the Pacific and then the rest of the globe. So that's very, very encouraging. We used later on similar simulations, but these are now really climate simulations, which are initialized in 1850 and then ran transcendently until 2021. Those are called IHASP simulation, together with Texas A&M University. What we're looking at here is extreme precipitation. This is something I work on a lot. And this is extreme daily precipitation. So this is the daily maximum precipitation within each year that you see here in the observations on the left and the top left. And then our 4 degree atmosphere and 1/8 or 1/10 degree ocean model in the middle. You can see those two maps match up quite well. So these models are getting quite close to simulating daily extreme rainfall rates globally, which is very encouraging. And then the 1 degree counterpart in the top right, and you can see those are very far off. And this relates or looks quite similar to the high-res-MIP simulations that you can see down below, where we see that the coarse resolution version, the CMIP6 models, they are under resolving or under representing the extreme precipitations, and then the high-res-MIP are much closer to that. So again, very encouraging results here. When you look at the region where we have the highest precipitation, daily precipitation accumulations and extremes, those are typical regions where we get organized convective storms that we call mesoscale convective systems. And maybe many of you haven't heard about these storms, but these are basically, this is a satellite observation here over the US, where you can see these cloud clusters where many thunderstorms organize over large scales, hundreds and thousands of kilometers. And then they build basically weather features that are quite large scale. For example, here, there's another one popping up. Let's see if this works. The central, yes, I think I killed it. No. And there is another one over the upper prairie region. These are very frequent systems that develop, and those are really hard to prioritize, because our typical idea of prioritizing deep convection, that we have an ensemble of of convective cells within a grid cell, and then we parameterize those, doesn't work here because these systems are really large scale. They actually, even in a 1 degree grid box, they span multiple of those grid boxes. They mix energy and momentum over large regions, and the parameterizations are really falling down. So you can see there's a slantwise overturning circulations in this MCSs that is really completely missing in coarse resolution simulations. When you look at observations again, like they are really important for the hydrologic and energy cycle of the globe. So what you can see here is the proportion of rainfall annually that comes from MCSs compared to the total rainfall. And everything that's orange or red has 50% of more of rainfall comes from these organized convective storms. You can see the tropics are really saturated. So the tropics are dominated by organized convective systems, and some regions in the mid latitudes, like the central US, but also the La Plata Basin in South America, are other hotspots. If you look at extremes, it's even more pronounced. Like if you're in a region where you have mesoscale convective systems, you almost can be guaranteed that those are the process that causes the highest extreme precipitation. So simulating them is extremely important in our models. So what we did in a follow-on study, we used a feature tracking detection algorithm. This is called the multi-object analysis of atmospheric phenomena. You can scan the QR code if you want to run this in a Google Cloud notebook. What this allows you is really to identify a large variety of atmospheric processes like cyclones, anticyclones, atmospheric rivers, mesoscale convective systems, frontal zones, and so on, jet streams, but also equatorial waves. And we use this algorithm to check if these high-resolution simulations have a better representation of mesoscale convective systems, and yes, they do. So that's very encouraging because this tells us that the improved extreme rainfall that we see in these models is really coming from a better representation of the process that causes this extreme rainfall events. So you can see here the frequency of MCSs. There's still some biases, but it's way better simulated than, for example, in the 1 degree model. And then we also looked at what phenomena is really producing the heaviest rainfall, the heaviest daily rainfall annually. And this is showing here in colors. If you're in the orange region, and there are many orange regions, specifically in the tropic, you can see that mesoscale convective systems are the most frequent extreme producer. Once you get to the mid-latitudes, you get more cyclonic contribution. And you can see how stark the difference here is. On the left is the observations, then in the middle is the high-resolution models, and then the right is the standard resolution models. And the standard resolution models are really, really far off from what we see in observations. And I would say there's really a regime shift or a step change once you get to 25-kilometer atmosphere, a 10-kilometer ocean simulation in how you represent these extreme producing phenomena. However, if you look at mean state biases, and this is now again looking at high-risk MIP, many of these mean state biases are still there. So the frustrating thing maybe is that the resolution alone is really not sufficient. So don't expect that just increasing the grid space or decreasing the grid spacing will remove all the systematic biases. It's often not the case. Sometimes it makes it worse, and I will show you some examples in the next slides. I worked a lot in the US, so I will focus now on two regions in the US. One is the Eastern US and the Western US. The Western US has a lot of mountains topography. The Eastern US has flat plains and these mesoscale convective systems. So focusing first on the Western US and the topographic effects. And what we see here, maybe I can go back. And this is very systematic in CMIP models as well. There's a systematic wet bias in this region. In the summer and in winter. So we can start with looking at the winter bias there. So it's a little bit slow. And we have a very nice observational network in the Western US called SNOWTEL. You can see how one of these stations looks like. These are typically in the region where we have the highest snow accumulation. And those are monitoring water resources in the Western US. And there are multiple precipitation measure devices there, including snow pillars, but also gauges and snow height measurements. So those are very high quality. I think this is really a unique data set globally that we can look at. What I'm showing you here on the left-hand side is now looking at the west. Oh, this is the Colorado headwaters, actually, with like the headwater region of the Colorado River. And you can see within one season, 27 to 28, how the precipitation accumulated in the Colorado region. And we wanted to reproduce this accumulation with the weather research and forecasting model, which is a regional weather and climate model. And at 36 kilometers, what you get, and this is very systematic across many models, you underrepresent how much precipitation and snowfall you have in these regions, quite a bit. So what you typically have is you have too little rainfall or snowfall on the peaks and too much in the valleys. And this is primarily because you don't resolve the topography well enough. If you go to 18 kilometers, you get closer to the observations, but once you are at 6 and 2 kilometers, so this kilometer range, you get very close to what we observe, which is really encouraging because this is really essential for water resource management in the Western US. So high resolution certainly gains a lot of value once you get into topography. And there it's primarily, of course, the interaction between flow and topography. And I'm showing you this on this example here. There are features called cross-barrier jets. They are studied quite a lot, also from an observational viewpoint. What you see in the top right figure here is from a field campaign in the 80s, actually, where they identified that when flow hits a mountain barrier and it cannot move over, it has to go around. And then you get this cross-barrier flows. And in the bottom left here, you can see the wind profile in low levels in our simulations, and you can clearly identify where the flow has to go around obstacles and where you can flow over. And this flow around and flow over introduces this characteristic patches in the precipitation that we also observe. So once you basically have to move around an obstacle, you get a peak in accumulation of precipitation. And once you get through the gaps, you have less precipitation. We can simulate this very well with our 4-kilometer model in this case. And you can also see that we can get this cross-barrier jets simulated very well. So once you get to this kilometer scales, this orographic flow interactions are much better simulated. And this is also true. We see similar things in the Himalaya regions, for example, and also in the Alps. So moving now from the winter season, this is typically winter rainfall in the Sierra Nevadas and also many places in the Western US into summer rainfall. And summer has a very different bias. So now we are in the convective regime, and this is also very systematic across many models. What we're looking at here is the general cycle of summertime precipitation. In the top left, the black line here is the observations that we have, and then we used again the weather research and forecasting model, the WRF model, at 36 kilometers. And WRF is an interesting model because you have hundreds of different parameterizations and you can test them out. And we did that actually, and what you see here in colors is if you change the deep convection scheme in these models, you can see how the model precipitation responds in the Western US during summertime. And you can see all of these changes, like you can tune the general cycle quite a bit, but all of these general cycles have a too early peak of rainfall. So most of them peak during noontime, and this is still an issue in current model generations. And then they have way too much rainfall. So they trigger convection way too easy. And that's a problem that's caused by two things. First of all, the frequency, like these models almost rain every day at noon. So this is typically referred to as the drizzle bias. So you have, and then when it rains quite with less intensity. So very different to what we observe in reality, where you have a short burst of rainfall in the afternoon and then it's dry again. Once we go to 4 kilometers with the grid spacing here, you can see that we largely improve these biases, not only the amount, but also the frequency and intensity. So this has large implications, not only for hydrology, but also think about surface energy balances, like the cloud cover is completely different in these simulations compared to the coarse resolution simulations. And just to show you, ERA 5 still has these issues as well, to a less extent than models, but you can still find these issues in ERA 5. So moving on now to this dry bias in the central US. And there I already talked about these mesoscale convective systems that are extremely important there. And there were big projects that focused on this dry bias in the central US. The first one was the CAUSES project in CMIP 5. You can see here basically what the biases look like in the CMIP 5 ensemble. So you have a dry bias and the warm bias. These are coupled. And they basically hypothesized, I would say, that this is caused by not well representing mesoscale convective systems. That's a high-level summary. If you move on to CMIP 6, you see that we didn't get very far So the same biases are still there. There was a similar study made. I think now they have a better understanding of the source of these bias. And they talk a little bit about the root depth and evaporation and so on. So we got a new supercomputer at NCAR. And we were really psyched because we know we can do MCSs quite well at 4 kilometers, so this kilometer grid spacing. So we thought if we do 4 kilometer over the US, we will eradicate this dry bias. So let's see what happened. Oh yeah, this is just to show you, to remind you MCSs are really important in this region. And this is just to show you, like at 4 kilometers, you have this really this regime shift in how you simulate organized convection once you get from 12 kilometers, where you have to parameterize deep convection most of the time, to 4 kilometers, where you get really very different looking precipitation field and cloud dynamics. So what we did, again, we tracked MCSs, we followed them in space and time, and then we counted how many do we have. And in this red box, which we call the central US, and this is from observations. We have very good observational data sets in the US, radar-based data sets. And you can see in summertime, June, July, August, almost every day you have an MCS there. That's why they are so important for hydrology. So with our new 4 kilometer simulations, new supercomputer, up to June, really happy. Like we're really close to where we should be, and then things went south. It's really frustrating. We didn't understand what happened there. In fact, the model biases were even worse than in the 36 kilometer counterpart. And I think the issue was really that these deep convection schemes are very much tuned to work with the wrong climate, and they're tuned to give you approximately the right precipitation in a region that's really problematic to simulate. Once you take away this parameterization, your model reveals all the ugliness underneath, and you get to a stage which is very unrealistic. So we had biases up to 8 degrees, 9 degrees, temperature, 50% too dry. This is a desert region in the US, and it basically propagated through the whole summer season. Of course, like as we are model users, model developers, WRF has many, many physics options. We started to tune. So we thought maybe the aerosols should cool down the climate there. And many of the regional models have a very poor representation of aerosols, and we're not the dominant factor here. Then we thought shallow convection. Yeah, like even at kilometer scales, shallow convection is not very well simulated. So we tried out many different shallow convection schemes. It wasn't the leading process here. Boundary layer scheme, like yeah, of course, summertime convective boundary layer is pretty complicated to simulate even at kilometer scales. Also, that didn't help a lot. So after trying around and analyzing a lot, we came to the conclusion there was a single process that was dominant, was missing. And this was hill slope dynamics, meaning groundwater flow. So in most of our models, and I'm almost sure in all of your models, you have land surface schemes that only have a column that only allow water to move in a vertical column. There's no lateral flow, and that's an issue. And it's not a big issue if you run at coarse resolution, because it don't seem like they don't resolve the slopes anyway. So if you're in a low resolution model here, for example, you have very shallow slopes. That's why the lateral flow of water in the surface is quite low. You get fairly deep water tables in the valleys, and also deep water tables in the top of the mountains. And then you don't get a lot of evaporation in this region. But the central US is a region, you can see this in this map, which shows you the water level depth, lots of dark green. These are very shallow water levels. And you can see all these mesoscale river valleys that we have there. And in these valleys, if you go to high resolution, the slopes are much steeper, the lateral flow is much larger, and then you get very shallow water tables in the valleys. And you get deeper water levels in the hills. And this is really increasing evapotranspiration in the whole region. So this is a very small scale process that has a big impact on the central US, but there are other regions like the La Plata Basin, Sahel region, Southeast Asia, where these processes are really important. If you include this process in the 4 kilometer simulation, you almost eradicate the whole bias, like the temperature bias is almost gone. We realized this was almost a little bit too aggressive, but because there are other issues there, like irrigation, agriculture, but this is the dominant bias that we had in our models. And once we introduced this groundwater scheme, you can also see the MCSs in the lower left figure lined up very nicely. So now we are running with this scheme all the time. This is just to show you the cloud field that we get out of these simulations. This is downscaling ERA 5 to 4 kilometers. With the Wolf model, we use spectral nudging. That's why the cloud fields are very nicely in the right location. But it's really hard to differentiate which one is the satellite and which one is the model. We still have biases, but if you're in the ISS, it looks pretty good. If you look close up, you can still see issues. So if you, oh yeah, there's this. There should be a map of the US down there, so I don't know why this is not showing up. But what I wanted to show you, if once you simulate or run this model and you have it well tuned and you have the relevant processes in there, you can simulate hourly precipitation extremely well. And this is what I'm showing you here for the Northeast region. So this is Maine and like just the Northeastern region of the US. Comparing to co-op stations, these are hourly precipitation stations that we have there. And stage 4, this is a radar data set that we have over the US. And you can see the red line, which is the Wolf model, lines up with the other data sets extremely well, even for the tails. This is also true for the Southeast. So this is Florida, the Gulf Coast. Higher precipitation values, hourly precipitation values, and the model is, I would say, at least as good as the satellite data set compared to the stations. Same for the prairie, so very different climates that we're looking at here, but the model holds up pretty well. The Great Basin, this is a very arid region, and now you can see the observations have quite a big challenge there because there's radar blocking, there are not that many radar stations, and there are artifacts in the radar data set. The Wolf model is pretty close to observation, so we're pretty happy with that. We spent almost 10 years in developing this Wolf version, and we really tuned it to the US. And then we thought, is this like, we want to go global. Does all this development in the US really help us somewhere else as well? Like, is this really only tuned for the US? So if we move the domain, for example, to South America, would we get the same benefits? So this is what I wanted to show you here. We basically used the same model version. We ran 20 years, although this is only for 1 year, but this is robust over 20 years over South America being a really challenging region because we don't have that many observations. We were lucky enough to find a network of hourly rainfall observations that you can see here in this map. And then we basically did the same plots, the PDFs. And what you see here, the red line is the 4-kilometer Wolf, the light red is a 24-kilometer version of Wolf, and then you have 2 observational data sets. ERA 5, which of course is reanalysis, is very far off, and then you also see GPM I-merge. And just looking at that, you would conclude Wolf is really out for nuts. Like, this is way too heavy rainfall. And I see this a lot in published literature, and many people make these claims, like these kilometer scale models are really overdoing extreme rainfall. And I think that is true, but not to the extent that we think it is if we compare it to satellite data sets. Because if you now add the stations into this plot, you can clearly see which of these data sets is closest to the observations. So this is just a warning, be careful. Like, just because something is labeled observations doesn't mean it's great. I-merge is a great product, especially if you look at it at daily scales, in my experience. If you look at it for hourly rainfall, you really have to be careful, especially for extremes. So what I showed you so far is mostly, I would say, the added value of downscaling. So we're looking at, if you increase the resolution, you get better mesoscale convective system, better extreme precipitation at the scale where you have these phenomena. I think the exciting moment that we are in now is that we really can look at the opposite as well. Like, what is I think EERIE is all about that. What is the impact of better resolving mesoscale processes on the larger scales? That is upscaling effect. And I'm coming from this, from the observational side. I already showed you this impact. I think this is what I would call an upscaling impact. Better simulating hill slope dynamics in the Central West, you really get a better representation of a large region in precipitation and MCS statistics. But simulating extreme convective outbreaks in the US also has downstream impacts on Europe. And this is, for example, one case where we observed that. What you can see here, the red lines here, is negative potential vorticity. You can see a convective outbreak right now happening in the US. So lots of these red lines, these were very heavy convective storms in the US. And then you see an anticyclonic wave breaking over Europe. So this was causing a heat wave in April in Europe, caused by very vigorous convection in the US. And these kind of patterns are often referred to as forecast busts because these forecast models, state-of-the-art forecast models, have really difficulties in simulating this downstream impacts of this severe convective storm outbreak. So our hypothesis here was that if we better simulate the storms in the US, we hopefully also get a better wave response over Europe. They did this only on this case. We want to do more of these studies. But basically, I think we were quite successful with that. What I'm showing you here is the GFS forecast, and you can see this forecast bust here. You can see that this wave breaking over the Atlantic here is way too shallow. We actually break cyclonically rather than anticyclonically in GFS, and you can see very amplified bias in the 500 hectopascal geopotential height. We can reproduce similar biases if we use the model for prediction across scale. So this is AMPAS. This is a newer model from ANCAR. That is a global model similar to ICANN, I would say. And then when we get to 15 kilometers and 3.75 kilometers, you can see that we can much better simulate this anticyclonic wave breaking, and the RMSE biases in the 500 hectopascal height are reduced. So this is, I think, very encouraging to see these results. Of course, this is only one case, and we want to do more and better understand the processes that are happening there. And I think those cases are extremely important because they are often connected to extreme events. Another nice study that showed added values, this one by Jude and Rios Berrios, and I probably have to hurry up because I want to get you to coffee at 11. This is looking at tropical precipitation, and this is showing you a GPM iMerge Huffmöller diagram, and you can see all these waves moving around in the tropics, or tropical waves. If you want to simulate them at coarse resolution, that's extremely challenging. Most models are struggling there. You can see that the 120-kilometer version, this is again using the AMPAS model, has a very different tropical precipitation than what we observe in iMerge. Whereas if you go to 3.75 kilometers and you turn off the deep convection scheme, you get something much more similar to what iMerge shows you, and you get much better representation of tropical waves. What they did was a really interesting failure or error, I would say. Like they ran a 3.75 kilometer AMPAS simulation, but they forgot to turn off the deep convection scheme. Very costly mistake, but very interesting because you can see in the right bar here, this is showing you the variability of tropical precipitation and how the 3.75 kilometer simulation has a much closer variability to what we see in iMerge. But you also can see once you turn on the deep convection scheme, all this is gone. So the deep convection scheme is really harming your simulation, even if you go to high resolution. So finally, I wanted to also highlight this study here. One of the hopes once we got to kilometer scale global simulations was that we improve the double ITC set bias. This is one of the dominant biases that haunts us since many, many years. And you can see this in high-res MIP, for example, it's still there. So we went to, and this is now a very recent study, there's a preprint online. I encourage you to look at this. Using the ICANN model, I think this is 10 kilometer simulation, and you can still see in the ICANN model, without deep convection, you can do this at high resolution as well, it's still there. Like we still have a double ITC set, very noticeable here in the Western Pacific. Coupling to the ocean doesn't help. Like it's still there. Like it's really frustrating. Like even high resolution coupled, it's still there. And this study shows that changing heat fluxes in the ocean is like in ICANN at least, a very important process. So what they did here is there's a minimum wind speed when you calculate heat fluxes in the heat flux calculation, which is set to 1 meter per second by default. And they increased this to 4 meters per second, and suddenly this double ITC set was gone, and you had a much better representation of tropical precipitation. So again, just showing you, like resolution alone is not a solution for everything. Often these biases are really systematic, and you really have to dig deep into the model, find things like that, improve them, and then you get a better representation. But it's often the combination of high resolution and these processes. So if you would do the same thing in a low resolution model, you wouldn't, sometimes you don't get the results that you would like to see. The shallow groundwater scheme, for example, is another good example for that. So I'm hurrying up just to show you some of the efforts that we are leading here at ETH. We have a big project called the Exclaim project, where we use the icon model and port it to Python with the goal to have a model that's very efficient in running on GPU architecture. And we have a new pretty big machine here at ETH called ALPS. It's currently the 7th largest, fastest machine globally. It's mostly GPU based, so we really need a model that's can leverage these new architectures. And the Exclaim project is really focused to do just that with the icon model. So this was the project outline when we started. The goals, as I said already, was really to have a code that's very portable, so you don't have to rewrite the code for every new HPC system that comes online. And I think we are very close to that. Our code is very portable. It has a very good performance on these systems. It's quite easy to use and easy to read because it's Python-based, and there is community support. What we are currently working on is some use cases. So what you see here as well, like we got delayed partly because this new HPC system took much longer to get online than we thought it would be. So we started with the icon Fortran code, and now we are halfway through to have the whole system ported to Python. We're working on use cases. The first one I showed you in the last animation, which was the exoplanet use case, but we are also running regional climate use cases here. And this is a nice animation that was done in collaboration with NVIDIA, which shows you a 500-meter simulation of the cloud field over the Alps, over a regional domain that's focusing on the Western Alpine region. And I probably don't show you all of that, but you can see quite nicely how convection is resolved. Still, if you look closely, you can still see issues there, but it's getting quite close to what we see in observations. If you look at the cloud field, but also in the precipitation and the processes that underlie the simulations. So to summarize, when you look at high-resolution Earth system models, like the ones that you mostly use here in EERIE, like 20-kilometer atmosphere, 10-kilometer ocean, you can get a lot of added value. It's like I'm focusing again on the atmosphere here, but you see a much better representation of extreme precipitation, for example, and the underlying processes that cause these extreme precipitations. If you go to kilometer scales, you often get added value, especially in higher order statistics. Like, for example, the diurnal cycle of precipitation, hourly extreme precipitation rates are much better simulated, convective dynamics, orographic flow interactions, these kind of things. However, and I mentioned this a couple of times already, mean state biases are often still there. And you really need systematic model development to address those biases. Often it's really processes that are completely missing or tuned in the wrong direction because they were tuned to work with coarse resolution model setups. And the coupling, I think that's what you're doing here. I think this is extremely exciting. Many of these added value downstream impacts, we really see that they come out of this coupling. So we see a lot of interesting or encouraging results having mesoscale ocean eddies and how they respond, how the atmosphere responds to those. But we also, for example, I showed you this coupling to more realistic land surface processes. And I think this is a very encouraging field of research, and I hope that we can work together on this area. So thank you very much. I hope I didn't use too much time, and I'm happy to take any questions.